Perspective Class 8 Video 1. In this video I want to talk about parallel projection of lines. So I want to know what happens when I parallel project a line in three-dimensional space onto a two-dimensional plane. So begin by looking at this theorem, which gives you an answer. This theorem tells you that parallel projection sends lines to lines. So it sends a three-dimensional line down to a two-dimensional line, or sometimes it sends it down to a point. Okay? So why would it possibly send it to a point? I'll try and draw a schematic which gives you an idea of what's going on. So if I draw some coordinate axes x, y, and z, and I attempt to draw a viewing plane, so this is the plane onto which we're projecting, okay? Well, if I draw a line which is parallel to the y-axis, like this, then this whole line is going to get projected down. It's all going to get squished down to that one point right there. So this whole pink line, right, if you have the viewing plane over here, the whole pink line is just going to get squished down to a point like that. Okay? But it doesn't always get squished down to a point. Like if I have a more diagonal line like this, okay, then this line is going to get mapped like this. This line will get parallel projected down and it will form a new line like that. So the yellow line might look something like this. Okay, but the point is, parallel projecting lines in 3 dimensions always gives you a 2-dimensional line, or it gives you a point. So let's look at some concrete examples. So this question says, calculate the parallel projection of the line -2, 1, 3 plus t times 2, 1, minus 1 onto the plane z equals 0 and graph the image. Okay. Well, the first thing you do is you sort of rewrite the parameterization of the line. So the line is equal to -2, 1, 3 plus t times 2, 1, minus 1. I can rewrite this as a single vector. I can rewrite this as -2, 1, 3 plus 2t plus t, comma minus t, and I can rewrite that as -2 plus 2t, 1 plus t, 3 minus t. Okay, so this is still the equation of the line. This here, it's just another way of writing the same parameterization. And now I just apply the parallel projection to this single vector. So I have like this, and when I do the parallel projection, this gets mapped to -2 plus 2t, comma 1 plus t, comma 0, because I'm mapping onto the z equals 0 plane. So all I do is I replace the z coordinate with 0. Okay? So this is the projected line. It's a parameterization of the projected line. So now we should try and graph this line. Okay? So the first thing I'm going to do is just draw the coordinate axes. So it's on the z equals 0 plane, which means I have the x and the y. This thing here is the z equals 0 plane. Okay, and I want to graph this line, and I know that it's going to be a line, so it suffices just to find 2 points. And I'm going to find my 2 points just by plugging in easy values of t. Like if I plug in t equals 0, I have the point -2, 1, 0. And that point there is -2, 1. So it's that point there. Okay. And I could plug in another easy value of t. I could plug in t equals 1. You can use any value you want, but I'm just trying to use the easiest values because I'm not very good at arithmetic. So if I plug in t equals 1, I have -2 plus 2 times 1, which is 0. And then this is 1 plus 1, so this is 2, and then 0. So I have this point here. And now I know that because the answer is a line, I just connect these 2 points up like that. Okay, so this is the point that corresponds to t equals 1, and this is the point that corresponds to t equals 0. Okay, so I always forget, but I should have labeled my axes at least a little bit like this. Okay, and if you wanted, if the question asked, you could even calculate the equation of this yellow line. You could use the y minus y1 equals m x minus x1 equation, okay, where m equals y1 minus, well, I do y2 minus y1 divided by x2 minus x1. And if you do that and then you simplify, you should get y equals 1/2 x plus 2. But I'm not going to go through the details because we've spoke a lot about calculating the equation of a line in previous videos. Let's go on to a different example. So this example is a very similar looking question. Calculate the parallel projection of the line 4, 2, 3 plus t times 0, 3, 0 onto the plane y equals 1 and graph the image on y equals 1. So again, the first thing you do is you rewrite the parameterization. So I have this, which is equal to 4, 2, 3 plus 0, 3t, 0, which is equal to 4, 2 plus 3t, 3. And now I apply the parallel projection to this vector. So I apply the parallel projection, and I'm projecting onto the y equals 1 plane, so that just means I replace the y coordinate with 1. Okay, and this is the answer right here. And it might seem a bit strange because there's no t involved. There's no t. No t here. Okay, and that's because it's just a point. It's not a line anymore. It's just a point. Whereas in the first example, after the projection, we still had t's. We still had t's here. Now there's no t. And that corresponds to the fact that if I try and plot this on the y equals 1 plane, so that means this is x, this is z. If I try and plot this, then I'm just going to get 4, 3. That's it. Okay? So this whole line just squishes down to this 1 point right here. Okay? So this is the image of the line under the parallel projection. It gets squished down to 1 point. That's the end of this example, and that's the end of this video.